Dr. Mark Messerli from MBL's Eugene Bell Center. He studies the relationship between electrical fields and its application to human healing. He's going to walk us through a little bit of the history of the science that gave rise to Mary Shelley's Frankenstein, the ideas that are in that text. And he's going to give us a little glimpse of what's happening now in this field. So please welcome Mark Messerli.
Thank you. So I'm a scientist down at the Marine Biological Laboratory, and I'm interested in the physical cues by which tissues are built and maintain their integrity. And when I say physical, I mean mechanical forces that are involved and electrical forces that are involved. And you'll see that some of our research builds on the research that was done 200 years ago along the timeline with which Mary Shelley came up with the idea. It was motivated for writing Frankenstein. So for my presentation today, this phenomenon that the galvanism that Mary Shelley based her book on is also termed bioelectricity. So what is bioelectricity? I'm going to go over that. I'm also going to give you some well-known examples of bioelectricity. And then we're going to walk through history, hitting the major pioneers who helped us understand what we know now about bioelectricity. And finally, I'm going to discuss briefly a few of these therapeutic applications of electricity in the clinic. Okay, so what is bioelectricity? Well, first let's step back. What is electricity? So electricity is generally the separation or the manipulation of charge, positive charge and negative charge. We use electricity for passing power over very long distances via power lines, or saving power, storing it in a battery. Our electric cars, all of the electronic devices that you brought today are built on electricity. But nature also makes use of electricity, and this is termed bioelectricity. Bioelectricity is generated by living organisms, either at the cellular level, at the level of tissues, or at the level of organs. Okay? So there's a few fundamental aspects of electricity that I want you to know before we move forward. And one of those is about the charges. So opposite charges, the positive and negative charge, opposite charges attract, and like charges repel. It's a lot like dating in high school, if we all remember back. But one of the differences between bioelectricity and the electricity that we use in every day is that the charge moving through these power lines, or the charge moving through these batteries, are electrons. It's the electron, the negative charge on the electron that's passing. But in bioelectricity, the charge is predominantly ions, or salts. So sodium, chloride, potassium, it's the salts in the solution that are the charge carriers. So in this case, a negatively charged chloride anion will migrate toward the positive pole, the anode, and a positively charged salt ion, sodium, will migrate toward the cathode when an electric field is applied. Similarly, biological macromolecules, proteins or nucleic acids, are negatively charged, and they migrate toward the anode in an applied electric field. Okay? One other aspect which I want to describe is that when we talk about electric fields in biological applications, or bioelectricity, we're not simply talking about the voltage. We're talking about the voltage over a unit length. So if there was a single volt over a very small distance, that electric field would be very large, 1 volt over a very short distance. But if I took that volt and then spread it over a meter, well, the power between those two poles would be the field between those two poles would be much weaker. So the values that you'll be seeing later in the talk won't just be voltage. It depends on that voltage spread over a unit length. Okay? All right, so some specialized examples of bioelectricity. We're all familiar with the electric eel, which is a fish, but also the electric ray or the torpedo ray. So these two organisms can generate large electrical potentials outside of themselves, either 10 to hundreds of volts. And they use this to stun their prey, okay, or ward off a predator. They can also generate very weak electric fields that their bodies then sense, so that they can maneuver in very murky water or under very, very low light conditions. Similarly, other fish generate external electric fields, like the elephant nose fish or the knife fish. And again, they are generating these very weak external fields to help them navigate in very, very murky waters. So they have specialized organs which produce this electric field on the outside of their body, and then they have other organs which are being used to sense these very weak electric fields that they're putting out. Well, all of the cartilaginous fishes have electroreceptive organs. So a shark is my example here. They can sense the bioelectricity being generated by their prey. So when a fish is wiggling around and its muscles are contracting, and as you'll see in a moment, the muscles are generating this electric field outside of their body, the sharks can sense that. And so when sharks close their eyes just before they attack, which is why they've also commonly been known to bite down on corroded metals. I think one of the tanks up in Boston had a problem with the sharks swimming around and constantly banging into the wall because the metal was corroding and the shark was using that to navigate. But similarly, the monotremes, or a platypus, can sense electrical activity of its prey. So these are specialized examples of bioelectricity, but the more common bioelectricity, common to all living organisms, is an electrical potential across the plasma membrane. So all cells have a membrane on the outside, and all cells maintain an electrical potential across that. But this electrical potential isn't 9 volts like your 9-volt battery, or 1.5 volt. It's very small. In this example of a neuron, it's negative 70 millivolts.
Can you explain what an electrical potential is?
So an electrical potential is a separation of charge. And it's a measurement of the difference in that charge. So if there's a very large separation, in this case, between positive and negative charge, that's a larger voltage difference. So the voltage here then is the difference between the potential inside the cell compared to the potential outside the cell. Okay. So it's this electrical potential across the cell that is manipulated in neurons to send signals very long distances in milliseconds. Just as we use power lines and manipulate the electricity within the power line to move power over very long distances, our bodies in neurons, you manipulate electrical potentials on cells to send a signal. So if someone stepped on my foot real quickly, I'd know very rapidly. Okay? And so that's part of how nerve cells, or our nervous system, communicates to itself. But it also allows muscle to synchronize. So our heart muscle is an electric field is being generated by our heart when it contracts. And it's the propagation of that electric potential that is helping all those muscles to contract rhythmically and simultaneously as it propagates across the heart. And when you go in to have your heart checked, the electrocardiogram, they place electrodes, the 3 3 electrodes, either right outside your heart, or the 12-point electrode can go down to your ankle, because as your muscle is contracting and generating this electric field, that electric field is propagating through your body, and we're using electrodes put at different places to measure those electric potential differences, and it allows us to check the heart without cracking open your chest and finding out how it's doing. Okay, so it's a non-invasive method that we can use to see how the heart's doing. But skeletal muscle is similarly, when your skeletal muscle contracts, generating an electric field. And that's what the cartilaginous fishes, the shark, are sensing out there in the water. Imagine a fish that's just sitting there hoping that the shark won't see it, but that the electric field from its heart is giving it away. Okay, I also want to talk about a level of bioelectricity that's not as commonly, or at least publicly familiar, and that's one that exists across epithelia, or sheets of cells. And so skin is your largest sheet of cells, your largest organ in the body. There's an electric potential difference of 50 millivolts across the skin. Your cornea is an epithelia, the lining of your lungs, your gastrointestinal tract, the bladder. All of these sheets of cells generate electric fields across themselves. In fact, in the clinic, they're used to determine whether your nasal epithelia are functioning. It's called the potential difference method. They essentially place an electrode against the mucus in your nose, or against the epithelium in your nose. So your skin is acting like a battery. It's separating this charge. It's generating a 50 millivolt difference across the surface to the basal layer. When it gets injured, that battery short circuits and current flows through the wound, such that right in the vicinity of the wound, it generates an electric field that is quite high. Okay? And we'll come back to that in a little bit. So now let's walk through the beginnings of bioelectricity. And this starts in the late 1800s. About 10 years prior to my timeline here, we started to learn about electric fishes, that these fishes were generating these external electric fields. And we were also coming under control with static electricity. So an example of static electricity is the balloon rubbing on your head and then it sticks to the wall. So that's generating a static electric field. So this was being tampered with or tested in the clinic because we knew it changed heart rate, it caused sweating. But even then, the physicians at the time were writing, we have to be very careful with this, we don't know what this is doing. Okay? Luigi Galvani is one of these physicians, although Luigi, or we'll call him Galvani, was experimenting with electricity in his lab and was experimenting with building batteries. We had built capacitors by this time, an electrical component of circuits, but we had not yet succeeded in building batteries. So batteries are a source of charge. And so the story goes that Galvani was dissecting a frog, and two dissimilar metals contacted. Those two dissimilar metals created an electrical discharge through his scalpel. That was one of the metals, was his scalpel. And it arced, electrical arc, onto the frog leg, and the frog leg jumped. Well, he and his assistant experimented further and were able to repeat that. And Galvani explained that this was some force within the frog, some component of the frog that made this happen. Well, Alessandro Volta, Galvani's colleague and competitor, didn't think this was the case. So Alessandro Volta had come much further with building this voltaic pile, which in fact was our early battery. So Alessandro Volta repeated these experiments on the frog and explained and showed that it was the electrical potential from this battery that was generating this stimulation of the frog muscle. Of course, back then, the idea was that if you cut a frog in half, it's dead, right? And for all intents and purposes, it was dead, except the tissues, the organs, were not dead. You know, we've got thousands of organ donors that will testify to this these days, that that muscle, the nerve and the muscle in the frog leg was still alive. So what Galvani had accidentally done was taken a natural electric field that existed within humans, artificially produced it, and stimulated the muscle to contract with this artificial method. So the next 20 or 30 years takes us to Galvani's nephew, who was his assistant. So Galvani's nephew took these experiments, these frog experiments, and started doing them on humans. Although Aldini, Giovanni Aldini, had the tendency to want to do these in public forums. And a very famous one occurred in England after the execution of a tried murderer, of a convicted murderer. And this artwork shows the reaction of the people who were viewing this. So Aldini was simply trying to understand on a fresh cadaver whether the electrical application or electric field application could revitalize someone who had suffocated. So he was doing simple experiments. However, he was doing these simple experiments in front of a huge audience on humans again. Someone else at the time, Luigi Rolando, was also using cadavers and using electrical stimulation on the brain to characterize how the brain was controlling the rest of the body. And of course, you know, the brain is controlling the muscle movements in the rest of my body, and so by applying electrical application to the brain, body parts would twitch. I should go.
In a dead person?
In a dead person, but in a fresh cadaver. We call it a fresh cadaver, but you see the oxymoron there. In Aldini's case, this very famous episode, the cadaver's eyes open because he was doing electrical work on the facial muscles, and the muscles were twitching, and then arms were starting to move. Anyway, this was around the time that Mary Shelley was. These were the things that were going on around the time when Mary Shelley was motivated to write Frankenstein. Okay, and there is clearly no mention of electricity in the book, but it's notes that she made afterwards about galvanism, okay? And bioelectricity was named after Galvani, its founding father. Okay. But it wouldn't be until another few decades that the bioelectricity would be legitimized. So all of this was all the prior work was using electricity to stimulate muscle contraction. But it wasn't until Émile Dubois-Reymond built the first device to measure the electric fields that he started to standardize this system, this practice. Because what had happened was, while Galvani identified that an electrical stimulation could activate muscle, what he also did was inadvertently identified a device that could sense electricity, the frog leg. And so for decades, people had been using the frog leg as a galvanometer, a way to measure either electric potentials or electric current. It's not like today where we can go down to the Radio Shack and pick one of these devices up. So Dubois-Reymond recognized we have to standardize this experimentation. So Dubois-Reymond's thesis, his graduate thesis, was studying the electric fishes. What were they sensing? In order to see that, he needed to build a device to do this. And so he built the first galvanometer for measuring bioelectric phenomenon. He's also credited with measuring the first action potential, or the electrical propagation along a neuron. And he identified that the electric fist discharge is fundamentally similar to the excitation of nerve and muscle. And you can see here's a photo of him using his galvanometer on himself, which at that time was a common occurrence. Okay? But what Dubois-Reymond also measured about 150 years ago was the injury currents near skin. When skin is broken, that there's an electric field and a current leak that occurs near skin, and other damaged tissues like neurons or clusters of neurons. I just want to bring to your attention that there was a biography written on Dubois-Reymond, and it came out just last November, talking about some of the other peculiar historical occurrences, and more peculiarly, why such a famous scientist was forgotten. From all of the things that he had identified, why is he not in our textbooks as much as some of these other scientists? Okay. All right, so getting into the 20th century, we come to the MBL. So our expert at the time was Kenneth Cole, known to his friends as Casey Cole. Similarly, Casey Cole brought his electrical device to the MBL to characterize electrical properties of many different types of cells, including the squid giant axon. Then Alan Hodgkin came from England to meet with Cole to learn the use of the squid giant axon, took it back to England, and with his student Andrew Huxley identified the chemical basis for electrical propagation of the action potential in neurons. And they, along with Eccles, received the Nobel Prize in 1963. Okay, if we step back in our timeline a little bit, the first use of an electrical defibrillator was used in a hospital on a patient in 1947. This was 150 years since Galvani had first used electrical stimulation to get muscle to contract. And in this case, it saved the life of a 14-year-old patient who was undergoing some form of internal surgery, and his heart had started to beat arrhythmically. They had massaged the heart for 45 minutes and had not gotten it to beat rhythmically again. Someone go out and get these electrodes, which they had been using on dogs or experimenting on dog hearts at the time, but this was the first time. So 150 years from discovery to use in the clinic. Okay, but all these works together, the neuro work at the Marine Biological Laboratory was the beginning of the modern era of neuroscience. And the MBL would be the heart of this neuroscience field for the next 30 years. But we have to go to the 70s and 80s before studies on the electrical potential of the skin were to continue. So clinical trials start using electricity to heal wounds started in 1970. My academic grandfather, along with my undergraduate advisor, mapped the electric potentials across the human skin, and along with development of another electrical recording device, started measuring electricity around the surface of other organisms. In this case, this is a frog embryo. So it's an outline of the frog embryo, and these arrows are indicating current influx in the skin and then current efflux through the blastopore, which is the opening to the gut of the embryo. So again, we're looking at electrical devices that were advancing our knowledge. Why are we so interested in the skin at this point? It's because of the chronic wounds. So, sorry, I had that. Chronic wounds are wounds that have not healed within 30 days. Okay? They commonly afflict the elderly or the bedridden, diabetics, and people with zinc deficiency. Okay? The treatments cost the nation $20 to $25 billion annually, and this is generally the bandages. The constant change of the bandages is a large part of that. But many advanced therapies are expensive, such as skin grafts or skin substitutes, and aren't suitable for use on diseased or elderly patients. So let's go back to the bioelectricity across the skin. The healthy skin maintains a 50 millivolt potential across it, and the injured skin leaks the current, so this battery that's generated across the skin leaks. And right here, underneath the epidermis, the positive pole is our anode, and at the center of the wound is the cathode. So remember that the center of the wound is the cathode, or the negative pole. Okay, how strong are these electric fields? So we're using the units of millivolts per millimeter. So this is the field, so about 100 to a few hundred millivolts per millimeter is used for defibrillation in the heart. In order to punch holes in cells, which we use for little tricks in biology, you have to go up another couple orders of magnitude, 100 to 1,000 times greater. This electric field across the plasma membrane is about 1,000,000 millivolts per millimeter. And if you take that out, that's about 1,000,000 volts per meter. An incredibly powerful electric field that exists across the plasma membrane. And of course, down here, about 1,000 and 1,000,000 times smaller are the electric field that our shark and platypus beak can sense. The electric fields around a wound are right here in the middle. Okay, between the lowest that some of our organisms can sense, and certainly well below the maximum field across the plasma membrane. So it's about 100 millivolts per millimeter, and the sensory threshold for these cells is about 7 millivolts per millimeter. But what do these electric fields do? When we apply electric fields to cells in a dish, what does it do? Well, we know it changes the gene expression. And during wound healing, certainly the cells that are sitting there all nice and stationary have to start migrating to the center of the wound, and that's accompanied by changes in gene expression. The electric fields also increase the rate of cell division. So again, in a wound where the cells need to be replaced, that natural electric field is strong enough to increase the rate of cell division. It orients the plane of cell division, but more importantly, for biologists and engineers, or tissue engineers, these very weak electric fields can direct cell migration and neurite outgrowth, or neuronal growth. Okay? So cells in culture, cells in skin, will migrate faster to close the wound when the electric field across the skin is increased. Neurites in culture will grow toward the cathode. This gives us a powerful tool for building tissues, for rebuilding tissues and organs for transplantation. Because our bodies aren't just a bunch of cells thrown together and working. You can't just take single cells, throw them on a wound site, and expect they'll do their job. Epithelia, or sheets of cells, are highly polarized from the apical to the basolateral layer. Neurons fire action potentials in only one direction. They're highly polarized. And muscle, skeletal muscle, cardiac muscle, the cells are aligned side to side and end to end to sum that force of contraction. So when we think about rebuilding tissues, we need to think about imposing this level of polarity to give us a structure that works like it's supposed to. So like the pioneers in bioelectricity, I make use of fish and frogs. So the fish, a scale can get plucked off a fish relatively unharmed, the scale gets placed down, and the cells migrate off. And we can study how the cells crawl along the bottom of our culture dish. And the frogs are really great for studying the electrical aspects of the skin. And in this picture, we can easily place a glass microelectrode through the skin to identify what is creating this charge, what proteins, what biological macromolecules are involved with generating the electrical potential across frog skin. So this is just the the embryo at this point has 2 layers of cells. Okay, we can also do a number of other tests and tools that the frog and the fish have been designated for. Okay. But what happens when you take some fish skin cells, place them in a dish, and then apply a weak electric field across them? I'll let you decide. So initially they're migrating randomly, but then you see toward the end here that they all migrate toward the negative pole, the cathode. And if we take a photo of that somewhere in the mid-time, you see that the cells, they align their long axis perpendicular to the electric field, and they migrate. We can study this by looking at the trajectory plots, or the path that the cells migrate. So in the absence of a weak electric field, the path of migration is random, goes out in all directions from the point of origin. When we apply a weak electric field, you can see the paths of the cells starting to migrate toward the cathode, and with a larger electric field, 100 millivolts per millimeter, a majority of the cells are all migrating to the cathode very quickly. So this 100 millivolts is generally our threshold of study. We stay below that field strength, even though the field strengths near natural wounds can get up to 200 or 300 millivolts per millimeter. But this doesn't just work on single cells, it works on sheets of cells. And the graph here shows how the amount of turning involved with whether it's single cells or sheets of cells. And there was an article published just this month in Nature Materials, where instead of taking small sheets of cells as we did, they took sheets of thousands of cells and applied a number of different types of electric fields, different profiles of electric fields to get the cells to migrate. And so you can see this is Nature Materials, even though I would consider it biology or physiology, how cells function. The engineers are using these electric fields to manipulate the orientation of cells to build biological structures. So electric field application occurs in the clinic, as I indicated, since 1970. And in this case, a cathode electrode is generally placed on the wound, and the return electrode is placed further up the leg. I'll talk a little bit more about this in the next slide, but what I wanted to emphasize here is that although there are companies out there that build these devices, and they are being used in the clinic, we still don't know how it works. Okay? Decades of successful clinical trials have led the U.S. Department of Health and Human Services to provide a positive coverage decision for using electric fields to treat chronic wounds of stage 3, stage 4 pressure ulcers, arterial ulcers, diabetics ulcers, and venous stasis ulcers. The complexity that was involved with these clinical trials is this. The natural state of the electric field at the skin is steady, or what we would call a DC potential, a steady electrical potential. But the clinical trials involved a number of electrical stimulation protocols, or electric fields that were applied repetitively for microseconds at very high potentials, hundreds of volts, or tens of milliamps. So the DC electric fields, low voltage, low current, is what naturally exists. And there were clinical trials with this application that enhanced the wound healing of chronic wounds compared to their controls. But so did all these electrical stimulation protocols, variations in all sorts of parameters. So someone these days could go get a treatment in one clinic, go to a different clinic, and get a very different treatment. the overall analysis of all these clinical trials stated that there is clearly an effect. There is a significant effect that it improves wound healing, but that whether, which one of these protocols worked the best on a particular problem was not known. So the electrical stimulation therapy was born out of the natural properties of the human skin. However, the electrical stimulation is very, very different from the electric field that exists in the human skin.
I would have thought while you were talking that I had surgery on my head, so I had a couple of open wounds, and the occupational therapist was using that stimulation.
They call it STIM.
STIM, yeah. And so I can understand how this cells would neurons would migrate to the catheter.
Right, to the center of the wound.
Right, but then I had physical therapy for a shoulder thing, and there was no wound, but they used the stim, and I wonder how the cell would migrate.
Okay, no. So was the therapy on muscle, bone, cartilage?
Muscle.
Okay, so in this case, it turns out that some of this electrical stimulation, as used on skin, was born out of the fact that they were using it on patients with bed sores. And of course, the patients who had developed these bed sores were quadriplegics or paraplegics. So they would hook them up to keep the muscle active, and that was charging the skin as well, and it appeared to heal the wounds. So again, without knowing how it's working, it's being used. So alongside of these more recent studies on skin were studies on spinal repair. And so these were done or pioneered by Richard Borgens at Purdue University, and they first started with lamprey. So lamprey is one of these lower branching vertebrates that can repair its spinal cord to some degree. And their first experiments were to apply an electric field along the axis of a transected spinal cord. And what it did was it enhanced the rate of healing. So we know lamprey can heal, but the application of an electric field sped the rate of healing. So that after a few weeks, there were many more connections in the experimental animals than in the control animals. So these early experiments then led to experiments on mammals, the guinea pig, dogs that were naturally injured. So Dr. Borgens is at the vet school, and so dogs that had accidentally been hit by cars were brought in, randomly allocated to different groups. And then it was in 2005 that the first phase 1 clinical trials were performed on humans. So again, humans that were had spinal accidents. Now the phase 1 trial is just for safety and tolerability. And the device that they developed is now controlled by a company here in Massachusetts. Now, the FDA wished for more phase 1 clinical trials, and this was put on a back burner for this company. Oscillating field stimulator. So in summary, nature has plenty of uses for bioelectricity. Our research continues to build on the historical finding of our predecessors, the pioneers, 200 years ago, and our results have direct impact in helping to promote human health and promote or cure disease. But there's still a lot we don't know, but we are working on it. I want to thank the National Institute of Health for helping to fund our research, along with the Eugene and Millicent Bell Fellowship Fund and the Herman Foundation. Thank you for your attention.